a bar, and we're going to talk about the properties of this bar, like we did yesterday. I believe at the end of yesterday, we had talked about the relationship between linear values and angular values. True enough? So I wrote something on there like velocity equals angular velocity times the radius. Do you remember this from yesterday? Just to make sure that we have everything from yesterday, did I talk about linear acceleration and its relationship to angular acceleration? Did I make clear that these are tangential and that we do have radial forms of acceleration, and that one radial form of acceleration is the centripetal acceleration? And hopefully before the bell rang for lunch, I probably indicated something like we can actually relate all of these things together, and that if you're particularly smart, you might want to be able to go home and prove that things that are rolling also obey this principle. I may not have said this next thing, but I want to make sure that's in your notes. This only works when these are in radians. Any calculation that utilizes an angular value and linear values, any calculation where I have angular values and linear values, you have to have your value in radians for it to work. So the kinematics equations you don't, but these you do. So what I'd like you to do now is kind of focus just on one of these. Because we're talking about kinetic energy is about velocity. So let's take this bar, and the bar we were using yesterday and today, we spun about the center of the object. So I'm going to continue with that and say that it's spinning like this, which means that it has an angular speed that causes it to move like that. Okay? I want to pick 3 different pieces of this object. I'm going to say that there's a piece here, a piece here, and a piece over here. 3 distinct pieces of the object. And I'm choosing these pieces because I want to consider that I know things about energy already. I know that kinetic energy equals 1/2 mv squared. But we just saw that clearly there must be a form of energy that is related to rotating. Right? We just saw the same example between the Atwood machine and the spinny thing. We saw the conversion of gravitational potential energy into motion. So the rotating object must have some kind of rotational energy. I want to find a way to talk about it. And one way to talk about it is to say that, well, this little piece has a velocity. So this little piece must have kinetic energy, 1/2 m1 v1 squared. And this little piece had velocity, say v2. And I know that its velocity, or its kinetic energy, must be 1/2 m2 v2 squared. And lastly, this piece must have a velocity, I'll call that v3. And it must have kinetic energy 1/2 m3 v3 squared. Now I know I could continue this on, and eventually I could cut my object up into lots of little pieces and talk about every piece's kinetic energy. But I think I've made my point enough that let's just look at these 3, and we could probably imagine looking at it in more pieces. Does that make sense? So the kinetic energy of our system right now would be the sum of these things. And I know that you know this, but I want to just state it out loud. I can add up all the kinetic energies of the individual pieces, and that has to be the kinetic energy of the system, right? The Atwood machine. If I wanted the kinetic energy of the system, I would have added up the bob that was falling, its kinetic energy, and the cart on the table. I'd have to add those 2 kinetic energies together to get the total. So if I break this up into lots of pieces, if I can add up each one of them's kinetic energy, I'm getting the total amount of kinetic energy. So I have 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 V3 squared. This is the kinetic energies of those pieces. Now, I know where the axis of rotation is. Because of that, I have a way to measure R1, and I have a way to measure R2. I'd even go as far as to say I have a way to measure R3, although it being on the other side of the axis kind of makes it negative, right? R's are vector values. They indicate how far away from the axis I am. Two of them are on the right, but one of them's on the left. So please keep in mind that this one is probably negative if these guys are positive. It's going to be important for something I'm going to bring up in a minute. And what I'm going to bring up is this. The entire object has the same rotational speed. If I want to try and get as many common variables together as possible, it would be nice to take this and write it in terms of the rotational speed, since the whole thing has the same rotational speed. So I'm going to do that. I'm going to say that I have 1/2 m1 omega r1 squared plus 1/2 m2 omega r2 squared plus 1/2 m3 omega r3 squared. Good so far? I'm going to do one more thing, and you might not understand why, but I do have a point I'm trying to get to. I'm going to pull out the 1/2 out here in front. And at the end, I'm going to pull out the omega squared there. Right? Every term has a 1/2 in it, so I pulled the 1/2 out to the front. And every term has an omega squared, so I'm going to pull it out to the back. And what I'm left with inside these parentheses would look like this. m1 r1 squared plus m2 r2 squared plus m3 r3 squared. And is it clear to you that I left room for all the other pieces that I didn't include here? So if I wanted the kinetic energy of the entire object, I could just keep going to each piece. What I would really need to know then is how much each piece weighed and how far away each piece is from the axis. That's what those two things mean. The mass of each piece, bless you, the mass of each piece and the distance from the axis to that piece. I'm going to point out some characteristics here that you're not thinking about, that I told you to keep in the back of your mind. All of the things in there are positive, because even the values that would have been negative, like R3, get squared, so they become a positive number, which means it doesn't matter which side of the axis the piece is on. It contributes the same. It just depends on how far away it is from the axis. But also, it means that this piece contributes more than this piece, right? When I look back in my picture, if they're nearly the same size, which piece is further away? The one that is close to the R2 or R1? So that one's got to be the one that contributes more to this. And if you look at what we have here, and I'm going to kind of go like that, we have something about the velocity squared here. All of this is how inertia, is expressed. Duck my head and hope they don't crowd out the urinals too much, right? All right, so this is this is how we deal with inertia for rotating objects. And I know this isn't obvious, but what I really want you to think about is I chose a bar on purpose because it was easy to see and we had one in front of us. But what this is telling me is that it doesn't really matter what my object is. This could be my object. I don't know, what is that? A bean? Okay, so this is we have a bean. We're going to spin a bean about this point here. If I wanted to think about the three pieces of the bean, I could think about a piece over here, a piece over here, and a piece over here. This could be M1, this could be M2, and this could be M3. Do you realize that I would get the same relationship for inertia here? That even though R1, R2, and R3 are all in different directions, because they're squared here, it's not about what direction they are, it's just about how far away they are. Any information about direction would have been lost when I squared it, in the same way that the negative sign was lost when I squared the last one. So we call this sum. We call this the moment of inertia. That is the official name for it, and it's given the symbol capital I for moment of inertia. I don't know why capital I, probably because inertia starts with I. There's more than one way to express the moment of inertia, but if I wanted to express what I've just written in a formula, the formula would be a summation, because I am adding together things. And I'm adding together m times r squared. So I would have to label each one as being I, and I would start with piece 1 all the way to the last piece, n. And I would say take mass 1 times R1, then mass 2 times R2, then mass 3 times R3. But this is what the summation looks like. If I wanted to write this as a summation, it says take your object, break it up into n number of pieces, and add up mr squared for each piece. Just a quick aside, you have homework about this. Like 3 questions in your homework that just ask you to calculate the moment of inertia of a point mass system. That's what this is. This is how you calculate the moment of inertia of a point mass system. A collection of individual masses. Most things in nature are not point masses. But you can treat some things in nature like point masses. For example, we can treat the Earth and Moon like point masses if we're interested in the moment of inertia of the Earth-Moon system. That's something that we treat as point masses. You can treat objects that are separated by distances. Like if you were holding onto a friend and you were spinning, when you were kids, you might do that. You guys could be treated as point masses. Anytime the axis of rotation is outside of the object, then the object can be treated as a point mass. I'll say that again. Anytime the axis of rotation is outside the object, then the object can be treated as a point mass. So if I put a ball on the end of a string and I swung it in a circle, the ball could be treated as a point mass. It's going around a point that is outside of itself. So there are plenty of legitimate uses for the point mass system. The problem is that most things in nature aren't point masses. I want you to consider the meter stick. And what I'd like you to do tonight is I'd like you to break the meter stick up into 10 pieces. I want to say that the axis of rotation is at the end, and I want you to act like you're breaking the meter stick up into 10 equal pieces. 1, 2, 3, 4, 5, 6, 7. Thank you. Cookies on the house, that's my favorite part. You're the best, Chloe, thank you. All right, so that's 9 pieces, but imagine I did 10 pieces. I want you to calculate the moment of inertia of a meter stick. Now, you don't know its mass, but you know that the mass of this piece is m over 10 because there's 10 pieces. Follow what I'm doing? Moreover, assume that each piece is a point mass with its mass at the center. So the first piece has a mass of m over 10, and its center is located, how far away is the center of mass for the first piece? Well, if the meter stick is 10, if each piece is 10 centimeters wide, then this first center of mass is 5 centimeters away from the axis of rotation. Does that make sense? How many pieces are there? So I can go to the next one. The next one has the same mass, m over 10. How far away is its center of mass? Well, the first piece is 10 centimeters long, then I add another 5 to get to the middle of the second piece. You follow along so far? So you're going to have 8 more of these, one for each piece of the meter stick. And I think you can probably imagine the next one without having to do any real work, right? Can we just kind of understand that the next piece, same, m over 10. And what's this number going to be? 25, yeah. Okay. Do this tonight. Come back with m times a number, and we'll finish this tomorrow.